50 light years from Earth, a giant planet circles a star much like our Sun. Its year lasts just over 4 days. That alone was enough to change astronomy. When 51 Pegasi b was discovered in 1995, scientists had spent decades building models of how planetary systems should form. Giant planets belonged far from their stars. That was where the material needed to build them was supposed to exist. Then astronomers found one practically skimming the surface of its sun. 51 Pegasi b has roughly half the mass of Jupiter, yet it completes an entire orbit before a week passes on Earth. It circles so close to its star that temperatures can climb beyond 1800 degrees Fahrenheit. This is not simply a hotter Jupiter. It belongs to an entirely different class of world, one that astronomers had barely imagined before they discovered it. A place where familiar materials can behave in profoundly unfamiliar ways, where metals can exist as vapor high in an atmosphere, where enormous differences in temperature can drive extreme winds around a planet that never experiences an ordinary day and night. And perhaps most importantly, a planet that could not have formed where astronomers found it. Something must have happened after its birth, something capable of moving an enormous world through its planetary system and leaving it trapped incredibly close to its star. Before 1995, no planet like this had ever been confirmed around a sun-like star. Afterward, astronomers began finding them everywhere. They became known as hot Jupiters, and their existence forced scientists to reconsider something much larger than one impossible planet. Perhaps our solar system was never the blueprint for how planetary systems were supposed to look. This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. To understand this, we need to go back to the discovery that changed what scientists thought a planetary system could be. Before we follow the planet any farther, it helps to pause our gaze on the star itself. Across a distance of 50.9 light years, in the constellation Pegasus, shines a sun that would never attract much attention on its own. Under a truly dark northern hemisphere sky, you can glimpse it without a telescope, though only just. With an apparent brightness of magnitude 5.49, it rests near the threshold of ordinary human vision, one modest point of light among countless others. Nothing about that star seems extraordinary. It belongs to the same spectral family as our own sun, meaning it shares a similar surface temperature, color, and overall character. Astronomers classify this kind of star as a yellow dwarf, one that spends billions of years steadily converting hydrogen into helium within its core. At roughly 5.9 billion years old, it has aged a little beyond the Sun's 4.6 billion years, yet it remains remarkably familiar. That familiarity mattered more than anyone expected. For decades, our understanding of planetary systems leaned heavily on the example surrounding our own Sun. A star so similar was expected to host a system shaped by comparable rules, with rocky worlds close in and giant planets far away. Instead, this otherwise ordinary star revealed something that fit none of those expectations. Even the planet's name reflects routine astronomical practice rather than importance. The letter following the star's designation simply marks the first confirmed planet discovered around it. Had another world been found first, the lettering would have changed, although the planet itself would have remained exactly the same. Names in astronomy often preserve the order of discovery rather than the scale of significance. Its orbit, however, demands attention. 51 Pegasi b circles at only 0.0527 astronomical units from its parent star. An astronomical unit is the average distance between Earth and the Sun, a convenient measuring stick for planetary systems. Mercury travels at roughly 0.39 astronomical units, leaving this giant world tucked dramatically closer to its star than anything in our own planetary neighborhood. The journey is astonishingly brief. One complete orbit requires only 4.23 days, carrying a planet with at least 46% of Jupiter's mass around its star in less than a single Earth week. Every physical process we examine from this point onward begins with that intimate orbital relationship. There is one final detail worth carrying with us. From Earth's perspective, this planet never crosses directly in front of its star. Astronomers call such an event a transit, and when it occurs, starlight filters through a planet's atmosphere before reaching our telescopes, revealing valuable chemical clues. Because 51 Pegasi b follows a slightly different path across our sky, that opportunity never arrives. We therefore combine careful observations of this remarkable world with discoveries from closely related planets, allowing separate pieces of evidence to assemble into one increasingly complete portrait. What does it actually mean for iron to rain on a planet? We usually imagine rain as water gathering into clouds before falling back toward the ground. Here, the same physical cycle unfolds with an entirely different substance, under conditions so extreme that one of the strongest metals familiar to us behaves more like humidity than rock. Iron reaches its boiling point at approximately 5,182 degrees Fahrenheit under standard pressure. Beyond that threshold, it no longer exists as a solid or even as a liquid. It becomes a gas. Across the blazing hemisphere of 51 Pegasi b, temperatures are believed to rise above that point, allowing iron from deeper layers and mineral material to enter the atmosphere as invisible vapor carried among the surrounding gases. Everything begins with relentless starlight. Energy pours into the day side without interruption, feeding immense columns of rising gas. Those upward currents, known as convection, transport heat by carrying hotter material higher, while cooler material sinks below. Along with that motion comes iron vapor, lifted far above the deeper atmosphere and swept into powerful global circulation. From there, the planet's upper winds take over. Instead of remaining above the blazing hemisphere, iron rich gas is pushed across the globe toward regions receiving far less stellar energy. The atmosphere itself becomes a planetary conveyor, moving enormous quantities of material from one hemisphere to the other in an endless exchange. As those currents reach cooler altitudes, conditions begin to change. Temperatures remain above 1,000 degrees Fahrenheit, yet they are low enough for iron to abandon its gaseous form. Tiny droplets emerge within the atmosphere, gradually growing until gravity takes command. Molten iron begins falling through layers of superheated gas, descending like metallic rain through clouds unlike anything found in our own solar system. The journey does not end there. Deeper beneath the visible atmosphere, temperatures climb once more. Before those glowing droplets can collect anywhere, the surrounding heat transforms them back into vapor. The cycle closes upon itself. Iron evaporates, rises, travels, condenses, falls, and evaporates again, repeating continuously without building oceans, rivers, or lakes. You are witnessing weather driven entirely by heat, circulation, and chemistry. For years, this remarkable process remained a carefully developed prediction. Then, during the year 2020, astronomers obtained direct evidence while studying another scorching gas giant called WASP 76b through spectroscopy, a technique that identifies substances by examining how they absorb specific colors of light. They detected abundant iron vapor along the boundary where the day side turned toward darkness, while the opposite edge showed almost none. The missing iron had already condensed and fallen from the upper atmosphere before completing the circuit. Iron is only part of this extraordinary mineral weather. Silicon compounds, magnesium silicates, titanium, and manganese are also expected to condense under suitable conditions, creating a planet where familiar geology has become atmospheric behavior. There is no landscape waiting beneath these storms, only layer upon layer of heated gas, forever reshaping itself beneath an unwavering star. Imagine standing at a place where the sky never changes. No sunrise arrives, no sunset follows. The position of the star above you remains fixed from one moment to the next, through every orbit and every passing age. That unchanging view comes from a condition called tidal locking, where a world's rotation takes exactly as long as its journey around its parent star, causing the same hemisphere to face the star at all times. Our own moon offers a familiar example, presenting the same face to Earth across billions of years. For 51 Pegasi b, this arrangement became inevitable. Orbiting at only 0.0527 astronomical units, the star's immense gravitational pull continually tugged against the planet's rotation. Those uneven forces gradually drained away its original spin, a process completed within only a few 100 million years. By the time the system reached its present age, the planet had long settled into its permanent orientation. Across the hemisphere, facing the star, energy pours downward without interruption. Surface temperatures remain between approximately 1,800 and 2,200 degrees Fahrenheit. The parent star never drifts across the sky. It never climbs higher or sinks lower. Every hour appears identical to the last, measured only by the passage of orbital time rather than any movement overhead. The opposite hemisphere experiences an entirely different existence. Direct starlight never reaches it, yet darkness does not bring relief from the heat. Atmospheric circulation continually transports enormous quantities of energy from the illuminated side, keeping temperatures above 1,100 degrees Fahrenheit. Even the absence of daylight cannot overcome the efficiency with which the atmosphere redistributes warmth around the planet. Between these two permanent realms lies a narrow boundary known as the terminator. This is the ring where perpetual daylight meets perpetual darkness, wrapping completely around the globe without ever shifting. Here, the temperature contrast becomes especially dramatic, producing fierce atmospheric mixing as scorching gases encounter much cooler air. Chemical reactions accelerate, clouds evolve, and the exchange of material between hemispheres reaches remarkable intensity. You might wonder how time would feel in such a place. On Earth, we divide our lives into mornings, evenings, seasons, and years because the sky constantly changes around us. Those familiar markers disappear here. There is no spring arriving after winter, no afternoon fading into night, and no yearly cycle that alters the angle of sunlight. The same hemisphere has faced the same star for more than 5 billion years. Life on Earth has always unfolded beneath moving shadows, changing constellations, and recurring seasons. 51 Pegasi b follows a different rhythm entirely. Time still passes, atoms still move, and the planet continues circling its star every 4.23 days. Yet nothing in the sky announces that passage. The landscape, the atmosphere, and the heavens remain locked into the same enduring arrangement, preserving one hemisphere in everlasting fire, while the other endures an endless stretch beneath an unlit sky. Air responds to differences. It always has. Whenever one region becomes hotter than another, pressure changes begin pushing the atmosphere toward balance. On Earth, that process gives us trade winds, hurricanes, and jet streams. Across 51 Pegasi b, the same physical rule operates under conditions so extreme that the resulting circulation becomes one of the fastest known weather systems in the galaxy. The hemisphere facing the star remains near 2000 degrees Fahrenheit, while the opposite side stays above 1100 degrees Fahrenheit. That enormous thermal contrast continually stretches and compresses the atmosphere. Heated gases expand, becoming less dense, while cooler regions draw material toward them. The atmosphere has no choice except to move, and it does so with astonishing force. Current models estimate upper atmospheric winds between roughly 5,000 and 9,000 miles per hour. Those speeds are difficult to picture without comparison. The strongest surface wind ever measured on Earth reached about 253 miles per hour during Tropical Cyclone Olivia in the year 1996. Even Earth's swiftest jet streams rarely exceed 275 miles per hour. Saturn, famous for tremendous atmospheric motion, reaches approximately 1,100 miles per hour around its equator. 51 Pegasi b surpasses every one of those benchmarks many times over. At the upper end of those estimates, the flow exceeds 11 times the speed of sound through Earth's atmosphere. Yet these are not isolated gusts or temporary storms. We are looking at a persistent planetary engine powered by uninterrupted heating, operating through every orbit for billions of years. The circulation organizes itself into what astronomers call an equatorial superrotation jet. Superrotation describes an atmospheric current moving around a planet faster than the planet itself rotates. Rather than simply rushing from the illuminated hemisphere toward the darker one before fading away, the winds wrap around the globe in a continuous high-speed band, transporting tremendous amounts of heat with remarkable efficiency. That transport creates an unexpected consequence. You might assume the hottest location would sit directly beneath the star, where incoming radiation strikes most intensely. Instead, the fastest winds carry heated gas farther along its path before it has time to cool. The peak temperature shifts eastward, displaced from the point receiving the greatest amount of starlight. In a sense, the moving atmosphere races ahead of the heating pattern itself. Astronomers have measured this effect on closely related hot Jupiters using observations from the Spitzer Space Telescope. By recording subtle changes in infrared light throughout an orbit, a technique known as a phase curve reveals how heat is distributed across a distant world's atmosphere. Those thermal maps consistently show the hottest regions offset from the point directly facing the star, matching predictions made by atmospheric models. As you follow these currents around 51 Pegasi b, there is no changing season to interrupt them and no cooling interval to weaken their momentum. The same global circulation has likely persisted for roughly 5 billion years, driven by the same relentless energy source, tracing the same path around a world where weather has become an enduring feature of planetary architecture rather than a passing event. Suppose you could descend into 51 Pegasi b without being torn apart by heat or pressure. You would never reach a shoreline, mountain, or plain. There is no solid landscape waiting beneath the clouds. Gas gradually becomes denser with depth, and the planet is organized into layers defined by pressure rather than by rock. Astronomers measure those layers using bars, with one bar matching the atmospheric pressure at Earth's sea level. The outermost region is called the exosphere. Here, pressures range from roughly 1,000th to 100th of a bar. The gas becomes extremely thin, exposed directly to intense ultraviolet and X-ray radiation pouring from the nearby star. Atoms of sodium, calcium, magnesium, and iron can lose electrons under this relentless bombardment, becoming electrically charged particles known as ions. These atoms drift through the upper atmosphere, leaving distinctive patterns in starlight that reveal their presence across unimaginable distances. Far below lies the photosphere, extending through pressures of roughly 1/10 to 1 bar. Although there is no true surface, this layer serves as the planet's visible face because it is where most of the escaping light originates. When telescopes observe 51 Pegasi b, this is effectively the depth they examine. What appears to be a planetary surface is actually a glowing atmospheric boundary with no solid edge beneath it. Descending farther brings us into the cloud deck, where pressures climb between approximately 1 and 10 bars. Here, the remarkable mineral weather unfolds. Iron droplets form, silicate particles gather, and magnesium compounds condense before beginning their downward journey. As they continue falling into hotter regions, those materials return to vapor, remaining part of an endless atmospheric cycle instead of accumulating into permanent layers. Pressure rises dramatically below this region. Between roughly 10 and 100 bars, temperatures continue increasing while the chemistry grows far more unusual. Hydrogen remains the dominant ingredient, yet many familiar molecules become unstable. Compounds containing titanium, vanadium, and other metals influence how the atmosphere absorbs and emits light, shaping the appearance astronomers detect from Earth. Beyond 100 bars, matter enters a realm unlike anything encountered in ordinary experience. Hydrogen gradually transforms into metallic hydrogen, a remarkable state created when overwhelming pressure frees electrons from individual atoms. Those liberated electrons move through the material much as they travel through copper wire, allowing hydrogen, the lightest element in the universe, to conduct electricity like a metal. Still deeper, models suggest a compact core containing perhaps 10 to 20 Earth masses of rock and ice compressed beneath extraordinary weight. Conditions there exceed anything naturally found on our own planet, forcing matter into forms that laboratory experiments can only begin to approach. If you continued descending, there would be no unmistakable moment of arrival, only ever greater pressure, greater heat, and substances changing their very nature, carrying you through a world where depth itself becomes the defining landscape. Far beneath the glowing atmosphere, beyond the clouds and mineral storms, another process unfolds beyond the reach of any telescope. You would never see it directly, yet its influence extends far above the visible layers. It begins where hydrogen is compressed so intensely that it behaves like a metal, becoming an electrically conducting fluid instead of an ordinary gas. That remarkable material does not remain motionless. Heat continues flowing upward from the planet's interior, while rotation keeps enormous masses of metallic hydrogen in constant motion. Whenever an electrically conducting fluid moves inside a rotating world, it can generate a magnetic field through a process known as the dynamo effect. The principle is familiar, much closer to home. Earth's magnetic field arises because molten iron circulates within its outer core, creating the invisible shield that surrounds our planet. 51 Pegasi b follows the same underlying physics with a dramatically different ingredient. Instead of molten iron driving the dynamo, an immense ocean of metallic hydrogen churns beneath crushing pressure. The conducting region is vastly larger than Earth's outer core, providing the ingredients for an exceptionally powerful magnetic engine. Theoretical studies suggest that many hot Jupiters could possess magnetic fields even stronger than Jupiter's own. That comparison carries considerable weight. Jupiter already produces a magnetic field, roughly 20,000 times stronger than Earth's, dominating an enormous region of surrounding space. If planets such as 51 Pegasi b exceed even that benchmark, their invisible influence could extend far beyond the atmosphere itself. The nearby star also generates its own magnetic field. Rather than existing independently, the stellar and planetary fields interact across the narrow gulf separating the two bodies. Streams of electrically charged particles flowing outward from the star encounter the planet's magnetic shield, creating a constantly changing boundary where energy and charged matter are exchanged. In some hot Jupiter systems, astronomers have observed unusually active regions on the parent star that appear linked to the orbiting planet, suggesting the magnetic connection leaves a measurable imprint upon the star itself. Another clue may travel across space as radio waves. Throughout our own solar system, interactions between magnetic fields and charged particles generate powerful radio emissions around planets such as Jupiter and Saturn. Similar signals are expected from hot Jupiters, produced where the stellar wind collides with the outer edge of the planetary magnetosphere, the protective magnetic region surrounding the planet. Measuring those radio waves would provide one of the most direct ways to estimate the strength of an alien magnetic field. Astronomers have already searched for such emissions from 51 Pegasi b. The challenge is formidable. Any signal reaching Earth is expected to be extraordinarily faint, hovering near the limits of present-day radio observatories. Future generations of instruments may finally detect that elusive broadcast. Even a magnetic field of tremendous strength cannot halt the atmospheric circulation we have already explored. The iron rain forms much higher, governed by heat and chemistry. Instead, the magnetic shield shapes the planet's outermost atmosphere, influencing how charged particles escape into space beneath the relentless radiation pouring from the nearby star, adding yet another unseen force to this extraordinary world. Nothing holds an atmosphere forever. Gravity gathers gas around a planet, yet light itself can slowly carry that gas away. Around 51 Pegasi b, the parent star does more than provide heat for extraordinary weather. It steadily erodes the outermost layers of the planet, atom by atom, through an ongoing process driven by radiation. The highest levels of the atmosphere absorb enormous amounts of extreme ultraviolet light and powerful X-ray radiation. Those energetic photons collide with hydrogen and helium atoms, transferring enough energy for some particles to reach escape velocity, the speed required to break free from a planet's gravitational pull. Astronomers call this process photoevaporation, meaning the atmosphere is gradually dispersed into surrounding space through the action of stellar radiation. This is not merely a theoretical prediction. We have already witnessed atmospheric escape around another hot Jupiter, a planet known as hydrogen delta 209458b, orbiting approximately 159 light-years from Earth, loses material at an astonishing rate, estimated in the tens of thousands of tons every second. Instead of remaining tightly wrapped around the planet, hydrogen stretches outward into an enormous tail resembling the glowing trail of a comet, extending away from the nearby star. The evidence came from observations by the Hubble Space Telescope. Rather than photographing the escaping gas directly, astronomers detected an immense cloud absorbing ultraviolet light as the planet crossed in front of its star. That cloud extended well beyond the planet's visible atmosphere, revealing that material was actively streaming into surrounding space while the world continued its rapid orbit. 51 Pegasi b appears to follow a less dramatic path. Although it receives relentless radiation, its substantial gravity holds on to most of its atmosphere. Current models indicate that the planet remains massive enough to resist catastrophic loss, preventing the wholesale stripping seen in more vulnerable worlds. Even so, resistance does not mean complete protection. Over billions of years, hydrogen and helium continue leaking away from the upper atmosphere in small but persistent amounts. That gradual escape shapes the long term evolution of many planets orbiting extremely close to their stars. Astronomers have proposed that some lighter, hot Jupiters may eventually lose nearly all of their gaseous envelopes, exposing the dense, rocky remnants hidden beneath. Such objects are known as chthonian planets, a name describing the stripped core left behind after an enormous gas giant has surrendered most of its atmosphere. This transformation may help explain a curious pattern discovered by the Kepler Space Telescope, where relatively few planets occupy the size range between large rocky super Earths and smaller gas rich subneptunes. For 51 Pegasi b, the future unfolds more gradually. Its gravity remains strong enough to preserve the overwhelming majority of its atmosphere today, yet the balance is never perfectly fixed. The parent star slowly grows brighter as it ages, increasing the energy reaching the planet with every passing age. The changes are almost imperceptible within a human lifetime, but across cosmic timescales, the atmosphere continues, yielding a little more of itself to space, carried outward by the very starlight that first shaped this remarkable world. Every star carries a future written into its own physics. We often think of stars as permanent fixtures, shining with dependable consistency across immense stretches of time. Yet, even the most familiar star is changing from the moment it is born. 51 Pegasi, despite its calm appearance today, is following the same evolutionary path that awaits our own Sunday. At approximately 5.9 billion years of age, the star remains on what astronomers call the main sequence, the long stage of stellar life powered by hydrogen fusing into helium within the core. This period lasts billions of years because hydrogen is abundant, allowing the star to maintain a remarkably steady balance between the inward pull of gravity and the outward pressure produced by nuclear fusion. That balance cannot last forever. As the central supply of hydrogen gradually dwindles, the core begins to contract beneath its own weight. Compression raises the temperature even further, while the outer layers respond by expanding outward. This transformation is neither an explosion nor an accident. It is the ordinary life cycle of stars like the Sun, unfolding over immense spans of time according to well understood physical laws. Current models indicate that within roughly 5 to 7 billion years, 51 Pegasi will leave the main sequence and swell into a red giant. During that phase, its radius may expand to between 1/10 and 2/10 of an astronomical unit, perhaps even farther, depending upon the details of its later evolution. That single change carries profound consequences for the nearby planet. 51 Pegasi b circles only 0.0527 astronomical units from its parent star. Its entire orbit lies well within the region that the expanding stellar atmosphere is expected to occupy. The planet will not simply experience stronger heat from a safe distance. It is likely to become immersed within the outer layers of the star itself. Once engulfed, the surrounding stellar gas creates drag against the planet's motion. Each orbit robs it of a little more energy, causing the giant world to spiral gradually inward. Over thousands of years, increasingly dense stellar material strips away the planet's outer atmosphere. The enormous envelope of hydrogen and helium disperses into the expanding star, while any surviving deeper layers continue sinking toward the interior. Eventually, even the compressed core should it remain intact for that long, is expected to dissolve into the star's vast interior. The iron that has cycled through the atmosphere for billions of years does not escape this ending. Those atoms ultimately become part of the star itself, mixed into its expanding outer layers before settling into the changing interior as stellar evolution continues. Long before that distant conclusion arrives, smaller changes steadily reshape the planet. As 51 Pegasi slowly grows brighter during the remainder of its main sequence lifetime, increasing radiation strengthens atmospheric escape and alters the chemistry already unfolding above the clouds. The transformation proceeds so gradually that no single generation of observers could witness it directly. This remarkable world has already endured longer than complex life has existed on Earth. It will continue its orbit for billions more years, remaining faithful to a star whose final act will eventually draw the planet into itself, completing a cycle that began when they first formed together. Imagine opening a textbook that explains how giant planets are born, only to discover a world that appears to ignore every chapter. Before the middle of the 1990s, astronomers regarded the leading explanation for planetary formation as both robust and remarkably successful. It was known as the core accretion model, and it accurately described the broad architecture of our own solar system. The model begins in the broad disk of gas and dust surrounding a young star. Close to the star, temperatures remain too high for many volatile substances to freeze. Farther away lies a critical boundary called the frost line, the distance where water, ammonia, and methane can solidify into ice. Those frozen materials dramatically increase the amount of solid matter available, allowing tiny grains to collide, adhere, and gradually assemble into increasingly larger bodies. Over millions of years, those rocky and icy fragments build a massive planetary core. Once that growing core reaches roughly 10 Earth masses, its gravity becomes strong enough to capture enormous quantities of surrounding hydrogen and helium. The result is a gas giant, wrapped in a vast envelope that soon outweighs the solid interior many times over. Our own solar system fits this picture remarkably well. The frost line lies near 2.7 astronomical units from the Sun, between the orbits of Mars and Jupiter. Jupiter circles at approximately 5.2 astronomical units, while Saturn travels even farther out at roughly 9.5 astronomical units. Both formed comfortably beyond the region where abundant ice could exist. Then astronomers measured the orbit of 51 Pegasi b. Its path lies only 0.0527 astronomical units from its parent star, almost 50 times closer than the location of our own frost line. At such a distance, the young protoplanetary disk would have been intensely heated. Ice could not survive there. Without abundant frozen material, there would be far too little solid mass to assemble the large core required for a Jupiter-sized planet. The surrounding gas would also remain hot and diffuse, making it far more difficult for a growing planet to capture and retain an enormous atmosphere. The implication proved unavoidable. 51 Pegasi b almost certainly did not form where we observe it today. Instead, the planet must have originated much farther from its star, in a colder region where the ingredients needed for giant planet formation were readily available. At some point after its birth, something altered its orbit on an extraordinary scale, carrying an object hundreds of times more massive than Earth deep into the inner reaches of its planetary system. That conclusion transformed a single discovery into a profound mystery. Planetary scientists no longer asked only how gas giants formed. They also had to explain how one could travel across nearly an entire planetary system without being torn apart, ejected into interstellar space, or plunging directly into its star. 51 Pegasi b did more than reveal an unfamiliar planet. It exposed an entire chapter of planetary evolution that existing theories had scarcely considered. The journey of 51 Pegasi b did not happen in a single dramatic moment. There was no violent collision that hurled the planet inward, nor a sudden gravitational slingshot that placed it beside its star. Instead, its path changed gradually while the planetary system itself was still young, surrounded by the broad disk of gas and dust from which every planet in the system originally emerged. Astronomers call this process planetary migration. For giant worlds such as 51 Pegasi b, the most likely mechanism is known as Type 2 migration. The name describes what happens after a growing gas giant becomes massive enough to reshape the very disk that created it. A protoplanetary disk is the broad, rotating cloud of gas and microscopic dust encircling a newborn star. Within this flattened structure, tiny particles collide, merge, and slowly assemble into planets over the first few million years of stellar history. Eventually, the young star's radiation and powerful stellar winds disperse the remaining material, ending the era of planet formation. Before that happens, however, the disk remains an active environment where planets and gas constantly influence one another. As a giant planet grows, its gravity becomes strong enough to clear a broad gap around its orbit. Rather than consuming all nearby material, the planet pushes much of the surrounding gas aside, leaving an annular opening within the disk. Fresh gas continues orbiting, both closer to the star and farther away, separated by the planet's newly carved path. Those remaining regions exert gravitational torques upon the planet. A torque is a twisting gravitational influence capable of changing an object's motion without direct contact. Gas inside the planet's orbit pulls one way, while gas outside the orbit pulls another. Although both forces act continuously, they do not balance perfectly. The outer portion of the disk generally exerts the stronger influence, causing the planet to lose angular momentum, the quantity that keeps an orbit stable at a given distance. As angular momentum gradually decreases, the orbit slowly contracts. Nothing about this migration is hurried. The planet drifts inward over hundreds of thousands or even millions of years, completing countless revolutions while its orbital distance steadily shrinks. Throughout that long passage, the giant world remains embedded within the evolving disk, moving because gravity continually redistributes momentum between the planet and its birthplace. The inward motion eventually comes to an end when the protoplanetary disk itself disappears. Radiation and stellar winds from the young star sweep away the remaining gas, removing the material responsible for driving migration. Without that surrounding disk, the gravitational exchange ceases, leaving the planet stranded wherever it happens to be at that moment. Current evidence suggests 51 Pegasi b reached its present orbit only within roughly the first 10 million years of the system's existence. Today, we understand that planetary migration is a common outcome of disk physics rather than an unusual exception. In that light, our own solar system appears increasingly distinctive. Jupiter's inward movement seems to have been limited, preserving the broad, stable region where Earth and the other inner planets eventually formed, while 51 Pegasi b continued traveling until the young disk released its hold. Long before 51 Pegasi b settled into the orbit we observe today, its path crossed a region where smaller worlds were still taking shape. Planetary systems are crowded during their youth. Countless rocky bodies, from pebble sized fragments to growing protoplanets, circle within the disk, colliding, merging, and gradually assembling into terrestrial planets over millions of years. That orderly construction can be profoundly altered when a giant planet begins moving through the same neighborhood. A world approaching the mass of Jupiter carries an immense gravitational influence. As it migrates inward, every nearby object feels that changing pull. Some developing planets are accelerated onto elongated paths that carry them dangerously close to the star. Others experience repeated encounters that increase their orbital energy until they are expelled completely, becoming wandering planets adrift between the stars. Many more are left on unstable, intersecting orbits where collisions become increasingly likely. Computer simulations suggest that the young 51 Pegasi system may once have contained several rocky protoplanets within its inner regions. Those bodies were probably following the familiar process expected around Sun, like stars, gathering material and growing through countless impacts. Had the giant planet remained beyond the frost line, some of those worlds might eventually have matured into stable terrestrial planets. Instead, the migrating giant swept inward through the very territory where such planets normally emerge. The habitable zone of 51 Pegasi, the region where temperatures could allow liquid water to exist on the surface of a rocky planet, lies between approximately zero point 0.9 and 1.7 astronomical units. Yet 51 Pegasi b now circles only 0.0527 astronomical units from the star. To arrive there, it almost certainly traveled across the entire interplanetary system, including the habitable zone itself. That passage would have reshaped the architecture of the system. Gravitational disturbances do not simply move planets aside for a moment before restoring the previous arrangement. Every altered orbit changes future encounters, producing a chain of interactions that continues long after the giant planet has moved on. Bodies that survive the migration often remain on highly eccentric paths, meaning elongated orbits that carry them alternately, much closer to and much farther from the star. Such configurations rarely remain stable over billions of years. For that reason, astronomers suspect the habitable zone around 51 Pegasi is probably empty today. The distance itself remains favorable. The challenge is the system's history. By crossing that region during its migration, the giant planet likely prevented long-lived, rocky worlds from ever becoming established there. As more hot Jupiter systems have been discovered, this pattern has appeared repeatedly. The presence of a giant planet hugging its star often points toward an earlier episode of migration that transformed the entire planetary system. The same gravitational process that delivered the gas giant inward also disrupted the environment where Earth, like planets, would otherwise have formed. In many cases, those two outcomes seem inseparable, revealing that the history of one extraordinary planet can determine the fate of every smaller world around it. Scientific revolutions often begin with measurements so small they seem almost insignificant. In the autumn of 1995, one repeating signal hidden within starlight challenged decades of confident understanding about how planetary systems formed. The observation did not arrive from a giant space observatory or a newly built planet hunting mission. It emerged from patient work carried out at an observatory in southern France, using an instrument originally intended for a different purpose. On the 6th of October, 1995, Michel and Didier Queloz announced their discovery during a conference in Florence, Italy. They presented evidence for the first confirmed planet orbiting a sun-like star beyond our own solar system. The claim rested upon data gathered with the Elodie spectrograph at the Haute-Provence Observatory, an instrument designed to measure tiny changes in the light of stars with extraordinary precision. The planet itself remained completely invisible. Instead, the astronomers relied upon the radial velocity method, a technique that measures the motion of a star along our line of sight. As a planet circles its star, gravity causes both objects to orbit a shared center of mass. The star, therefore, moves slightly toward Earth and then slightly away again. Those motions compress and stretch the wavelengths of starlight through the Doppler effect, the same physical principle that changes the apparent pitch of an ambulance siren as it passes by. Elodie was sensitive enough to detect changes in stellar velocity of roughly 43 feet each second, an astonishing level of precision for a ground-based instrument of its time. Within the observations of 51 Pegasi, a remarkably consistent pattern emerged. The star's velocity rose and fell with a period of 4.23 days, while the total change reached approximately 184 feet each second. The signal repeated with exceptional regularity. Didier Queloz encountered the pattern while analyzing observations for his doctoral research under Michel supervision. Rather than announcing the finding immediately, the team questioned it repeatedly. They collected additional observations over several months, searching for instrumental problems or natural stellar behavior that could imitate the signal. Every new measurement reinforced the same conclusion. Even after the public announcement, many astronomers remained unconvinced. Their skepticism rested upon sound scientific reasoning. A Jupiter-mass planet orbiting so close to a sun-like star contradicted the accepted framework of planetary formation. Alternative explanations seemed more plausible, including stellar pulsations, an unseen companion star, or subtle errors within the instrument itself. Independent confirmation arrived with remarkable speed. American astronomers Jeffrey Marcy and Paul Butler already possessed observations of the same star. After examining their existing data for a short period signal, they detected precisely the same repeating motion. The agreement between two independent observing programs rapidly strengthened the case. Within months, the objections faded as additional evidence accumulated. The measurements remained consistent, the planet remained real, and the accepted theory could no longer explain every planetary system. That single rhythmic wobble did more than reveal 51 Pegasi b. It marked the beginning of modern exoplanet science, reminding us that nature does not adjust itself to fit our expectations. Instead, our understanding must expand to meet the universe as it truly is. Light carries far more information than brightness alone. When astronomers collect starlight, they are also gathering a detailed record of the star's motion, chemistry, and physical conditions. The challenge is learning how to read that record with extraordinary precision. That is exactly what the Elodie spectrograph was built to accomplish, although its designers could scarcely have anticipated the discovery that would eventually define its legacy. Rather than recording a simple image of a star, the instrument spread incoming light into thousands of individual wavelengths. A household prism separates light into the familiar colors of a rainbow. Yet a scientific spectrograph divides those wavelengths with vastly greater detail. Dark absorption lines appear throughout the spectrum, each produced when specific elements inside the star absorb particular wavelengths of light. Those lines become remarkably precise markers that astronomers can measure again and again. To ensure those measurements remained stable, astronomers relied upon a carefully controlled reference. A glass cell containing iodine gas was placed directly in the incoming beam of starlight. Iodine naturally absorbs light at hundreds of precisely known wavelengths, imprinting an intricate pattern across every observation. Because those absorption features remain stable, they serve as a fixed measuring grid against which even the smallest changes in the stellar spectrum can be compared. As the star moved slightly toward Earth, its absorption lines shifted almost imperceptibly toward shorter wavelengths. When the star drifted away, the same lines moved toward longer wavelengths. Comparing those tiny changes with the stable iodine pattern allowed astronomers to calculate the star's changing velocity with astonishing accuracy, even though 51 Pegasi lies approximately 50 light years away. The scale of that precision is difficult to appreciate. Detecting the motion produced by 51 Pegasi b has often been compared to noticing a marble nudging a basketball from roughly 300 miles away. The motion exists, yet it is so subtle that every component of the instrument, from its optics to its calibration, must remain exceptionally stable throughout each observation. Even with that remarkable sensitivity, the radial velocity method has important limitations. It reveals how long a planet takes to complete an orbit, estimates its minimum mass, and determines the size of its orbit around the star. It does not directly reveal the planet's diameter, its detailed atmospheric composition, or many features that become accessible when a planet crosses the face of its star. 51 Pegasi b never performs that crossing from Earth's perspective. Its orbital plane is tilted just enough that the planet passes above or below the visible disk of the star during every revolution. Because no transit occurs, astronomers cannot study its atmosphere using the powerful transmission techniques now applied to many other hot Jupiters. Perhaps the greatest breakthrough was philosophical rather than technological. The necessary instrument already existed. The physical principles were already understood. Astronomers simply recognized that familiar tools could answer a question many believed had little chance of producing such an extraordinary result. Within only 5 years, increasingly refined versions of the same radial velocity technique had confirmed more than 50 planets around other stars, transforming a single discovery into an entirely new era of astronomy. A beam of starlight may appear perfectly ordinary when it reaches a telescope on Earth, yet hidden within that light is an astonishing amount of information. Every atom and every molecule interacts with light in its own distinctive way, absorbing or emitting specific wavelengths that no other substance can duplicate. Astronomers often describe these patterns as chemical fingerprints because each one uniquely identifies the material that produced it. When a planet passes directly across the face of its star, part of the starlight travels through the thin upper layers of the planet's atmosphere before continuing toward Earth. This technique is called transmission spectroscopy. Spectroscopy is the science of separating light into its individual wavelengths and studying the patterns within it. As the light filters through the atmosphere, certain wavelengths are absorbed by gases surrounding the planet, leaving characteristic gaps in the observed spectrum. By comparing those missing wavelengths with laboratory measurements, astronomers can determine exactly which atoms and molecules are present. 51 Pegasi b presents a different challenge because it never crosses the visible disk of its star from our perspective. Without a transit, astronomers must rely upon other methods. Reflection spectroscopy searches for the tiny fraction of starlight that bounces from the planet's atmosphere, while phase curve analysis measures how the combined light from the star and planet changes throughout the orbit. Those changing brightness patterns reveal how heat and reflected light are distributed across the planet, offering clues about atmospheric structure even when the world itself remains unresolved. In 2015, observations made with the high-accuracy radial velocity planet searcher spectrograph produced one of the earliest reported detections of reflected light from 51 Pegasi b. The measurements suggested that the planet reflected a surprisingly large fraction of the starlight reaching its atmosphere, a property astronomers describe as geometric albedo, meaning the efficiency with which a planet reflects light directly back toward an observer. Later studies revisited those measurements and reached more cautious conclusions. The reflected signal proved extraordinarily difficult to isolate because it was buried within the overwhelming brightness of the nearby star. Rather than revealing a failure, those revisions demonstrated how science continually tests its own conclusions, especially when observations approach the limits of available technology. While 51 Pegasi b remains difficult to study in this way, many transiting hot Jupiters have yielded remarkably detailed atmospheric inventories. Astronomers have confidently identified sodium vapor, potassium, water vapor, iron vapor, ionized calcium, titanium hydride, and carbon monoxide in distant planetary atmospheres, each detected solely through its unique interaction with light. The James Webb Space Telescope has extended that capability even further. Since beginning scientific observations, it has detected carbon dioxide, sulfur dioxide, methane, and water within the atmospheres of planets dozens of light years away, providing an unprecedented level of chemical detail. Each confirmed detection represents far more than a list of ingredients. From nothing more than carefully measured starlight, astronomers reconstruct clouds, temperatures, atmospheric layers, and chemical processes across worlds humanity has never visited, proving that light alone can reveal the hidden character of distant planets. For many years, the idea of iron rain remained a carefully reasoned prediction. The physics pointed toward its existence. Atmospheric models consistently produced the same outcome, and the extreme conditions on hot Jupiters made the process appear unavoidable. Yet science advances most confidently when theory meets observation. That opportunity arrived with another distant giant whose orbit offered astronomers a far better view. The planet is known as WASP 76b. Discovered in 2013, it circles a star approximately 640 light years from Earth. Like 51 Pegasi b, it belongs to the family of hot Jupiters, giant gas planets traveling remarkably close to their stars. One important difference changes everything. From our perspective, WASP 76b passes directly across the face of its star, allowing astronomers to examine its atmosphere through transmission spectroscopy with exceptional detail. Its environment is even more extreme than that of 51 Pegasi b. Daytime temperatures climb to roughly 4,350 degrees Fahrenheit, easily hot enough to vaporize iron into a gaseous state. The perpetual night side remains much cooler at approximately 2,730 degrees Fahrenheit. Although still unimaginably hot by earthly standards, those conditions allow iron vapor to condense into liquid droplets high within the atmosphere. In 2020, astronomers using the Michel spectrograph for rocky exoplanets and stable spectroscopic observations instrument at the European Southern Observatory Very Large Telescope in Chile examined the planet during transit. Rather than treating the atmosphere as a single uniform shell, they compared the chemical signatures appearing along opposite edges of the planet as it crossed its star. The observations revealed a striking imbalance. Strong absorption from iron appeared along the evening limb, the boundary where the blazing day side rotates toward darkness. On the opposite edge, called the morning limb, where the atmosphere returns from the cooler night side into daylight, the iron signal was dramatically weaker. That asymmetry carries an elegant explanation. Powerful winds transport iron vapor away from the intensely heated hemisphere toward the cooler hemisphere. During that journey, the vapor loses enough heat to condense into liquid droplets, which then fall deeper into the atmosphere before the circulating gas reaches the morning side. By the time that returning air comes back into view, much of its iron has already rained out. The changing pattern of absorption becomes a direct atmospheric fingerprint of an active iron rain cycle. The same observations identified additional mineral species within the atmosphere, including silicon monoxide, magnesium, and manganese. Together, they reveal an environment where multiple rocky materials exist as atmospheric gases before cooling into exotic forms of precipitation, unlike anything found within our own solar system. For worlds such as 51 Pegasi b, this discovery carried profound significance. Its atmosphere remains more difficult to examine because the planet never transits its star from Earth's viewpoint. WASP 76b demonstrated that the predicted chemistry was not merely a theoretical exercise. Iron rain had become an observable weather phenomenon, measured through light alone, confirming that such extraordinary meteorology is a genuine feature of hot Jupiters scattered throughout our galaxy. The first discovery naturally raised another question. If one giant planet could survive in such an unexpected orbit, how many others might be waiting among the stars? Once astronomers recognized that these close orbiting giants were possible, observatories around the world began searching with renewed purpose. Familiar stars received fresh attention, and existing measurements were examined through an entirely different lens. Hot Jupiters quickly became the easiest planets to detect with the radial velocity method. Their great mass produces a comparatively strong gravitational pull on the parent star, while their brief orbital periods repeat the same signal every few days instead of every few years. For astronomers, that combination meant reliable detections could be confirmed within months rather than decades. The results arrived rapidly. Within 5 years of the announcement of 51 Pegasi b, dozens of similar planets had been confirmed. What began as a single unexpected object soon became an entire class of worlds. The expanding catalog revealed that these giant planets were not isolated curiosities. They represented a genuine outcome of planetary formation, even if that outcome challenged established expectations. Early surveys suggested hot Jupiters might orbit nearly 1 out of every 10 sun-like stars. That estimate appeared remarkably high, although the available observations favored planets that were easiest to detect. As instrumentation improved and astronomers examined much larger samples, the picture became clearer. The National Aeronautics and Space Administration Kepler Space Telescope eventually monitored approximately 150,000 stars with unprecedented precision, providing a far more representative view of our region of the galaxy. Those observations substantially revised the original estimate. Current studies indicate that only about 0.5% to 1% of sun-like stars host a hot Jupiter. Expressed another way, roughly 1 out of every 100 to 200 similar stars possesses such a planet. At first glance, that fraction appears surprisingly small, yet the Milky Way contains somewhere between 100 billion and 400 billion stars. Even if only 0.5% possess hot Jupiters, that still implies hundreds of millions, and perhaps several billion, of these intensely heated giants scattered throughout our galaxy. Patterns also emerged within the stars themselves. Hot Jupiters are found far more often around metal-rich stars, meaning stars containing relatively large amounts of elements heavier than hydrogen and helium. Those heavier elements help build solid planetary cores more rapidly, while the protoplanetary disk still exists, increasing the likelihood that a giant planet can form before the surrounding gas disappears. Another trend proved equally revealing. Hot Jupiters are rarely accompanied by nearby planets. Their inward migration appears to have reshaped their surrounding systems, leaving few stable companions in neighboring orbits. The Kepler mission also revealed a broader perspective. Across the galaxy, hot Jupiters are greatly outnumbered by smaller planets known as super-Earths and sub-Neptunes, categories with no direct counterpart in our own solar system. When you compare those statistics with the orderly arrangement of our familiar planets, our own celestial neighborhood begins to look less typical than generations of astronomers once believed. By the beginning of the 21st century, astronomers had already proven that planets orbited other stars. A deeper question soon replaced that first triumph. Were those discoveries unusual exceptions, or were planets a fundamental feature of the galaxy itself? Answering that question required looking beyond individual systems and surveying an immense population of stars with unwavering patience. The National Aeronautics and Space Administration launched the Kepler Space Telescope on the 7th of March, 2009. Unlike earlier searches focused on finding remarkable individual worlds, Kepler pursued a statistical goal. It sought to measure how many Sun-like stars possessed Earth-sized planets within the habitable zone, the range of distances where liquid water could potentially remain on a rocky surface. Its observing strategy was remarkably disciplined. Kepler relied upon transit photometry, a technique that measures the tiny decrease in a star's brightness when a planet passes across its visible disk. Photometry simply means measuring light with exceptional precision. An Earth-sized planet crossing a sun like star blocks only about 1/100th of 1% of the star's light. Detecting such a minute change demanded extraordinary stability over many years of continuous observation. Rather than sweeping across the heavens, the telescope fixed its attention upon a single region of the constellation Cygnus, spanning approximately 115 square degrees of sky. Within that field, nearly 150,000 stars were monitored simultaneously for roughly 4 years. Every slight dip in brightness was recorded, compared, and examined for the repeating patterns expected from orbiting planets. By the conclusion of its primary mission, Kepler had confirmed more than 2,600 planets and identified thousands of additional candidates awaiting further study. More important than the growing catalog was the statistical picture emerging from those discoveries. The observations revealed that planets are astonishingly common throughout the Milky Way. Current estimates indicate that virtually every star is accompanied by at least one planet, implying the existence of hundreds of billions of worlds within our galaxy alone. The newfound diversity proved equally transformative. Kepler uncovered blazing lava worlds, planets likely covered by deep global oceans, compact gas dwarfs, super-Earths, sub-Neptunes, ultra-hot Jupiters, and many other planetary types, with no familiar counterpart in our own solar system. Each discovery broadened the range of environments that nature could assemble from the same fundamental ingredients. The mission also reshaped how we view our own neighborhood. Many planetary systems consist of several worlds packed into remarkably compact orbits, often fitting entirely within the orbital distance of Mercury. Despite their close spacing, these planets remain stable for billions of years through gravitational resonances, a condition in which repeated orbital rhythms help maintain long-term balance. Perhaps the greatest surprise is what our solar system lacks. Super-Earths, now recognized as one of the most common classes of planets in the galaxy, are completely absent from the planets circling our Sunday. Kepler, therefore, accomplished far more than counting distant worlds. It transformed planetary science from a search for isolated discoveries into an effort to understand the underlying patterns that govern how entire planetary systems emerge, evolve, and differ across the galaxy. Among the countless planetary systems now known, our own contains a feature that once seemed entirely ordinary. Jupiter circles the Sun at roughly 5.2 astronomical units, following an orbit that has remained nearly circular for about 4.5 billion years. Today, that arrangement appears less like a universal pattern and more like one possible outcome among many. Its location beyond the frost line allowed the young planet to gather enormous amounts of gas while the solar system was still forming. Equally important, Jupiter remained far from the region where the rocky planets assembled. Mercury, Venus, Earth, and Mars completed their long construction without a giant planet permanently occupying the inner solar system. For many years, astronomers suggested that Jupiter also serves as a protective influence. The idea became known as the Jupiter shield hypothesis. According to this proposal, Jupiter's immense gravity deflects many long-period comets before they can reach the inner planets. A long-period comet is an icy body that spends thousands or even millions of years traveling through the distant reaches of the solar system before returning toward the Sunday. By altering some of those trajectories, Jupiter may reduce the number of impacts reaching Earth. Modern computer simulations have revealed a more complicated picture. Under certain circumstances, Jupiter can also redirect objects inward, sending them onto paths that cross the orbits of the rocky planets. The planet therefore acts as both a gravitational barrier and, on occasion, a gravitational messenger. Astronomers continue to debate the balance between those competing effects. One conclusion, however, remains widely accepted. Jupiter never continued migrating into the inner solar system, leaving the terrestrial planets intact. Evidence for a more subtle journey comes from the Grand Tack hypothesis. In this model, Jupiter drifted inward during the earliest stages of solar system formation until it reached approximately 1.5 astronomical units from the Sunday. Saturn later formed farther out, and the combined gravitational interaction between the two giant planets reversed Jupiter's motion, pulling both worlds outward together. During that temporary excursion, Jupiter likely reshaped the asteroid belt and limited the material available to build Mars, helping explain why Mars is much smaller than Earth and Venus. Imagine the alternative for a moment. If Jupiter had continued its inward migration instead of retreating, it would have crossed the region where the rocky planets were still assembling. Developing worlds could have been scattered into deep space, absorbed by the sun, or consumed through violent collisions. The orderly arrangement we recognize today would almost certainly never have emerged. Astronomers have also noticed that cold Jupiters, giant planets occupying distant, nearly circular orbits, appear to show a modest correlation with systems containing inner rocky planets. The relationship remains an active area of research, yet it hints that certain histories of planetary formation may favor both stable giant planets and long-lived terrestrial worlds. When you place our solar system beside the extraordinary diversity revealed across the galaxy, its architecture no longer appears typical. Instead, it represents one successful configuration among many, a rare balance that allowed a rocky planet to endure for billions of years before producing observers capable of wondering why Jupiter stayed exactly where it did. Some discoveries answer old questions. Others change the questions themselves. The discovery of 51 Pegasi b belongs to the second kind. Its significance reached far beyond the existence of a single planet, reshaping one of humanity's oldest conversations about our place in the universe. Before 1995, asking whether we are alone was largely a philosophical exercise. Astronomers certainly believed that planets could exist around other stars, yet no confirmed examples circled stars like our own. Without observations of real planetary systems, discussions about life elsewhere rested upon assumptions that could not be tested against nature itself. Everything shifted once the first planet around a sun-like star entered the scientific record. From that moment onward, the search for life became anchored to measurable worlds rather than abstract possibilities. Every newly discovered planetary system added another piece to a growing body of evidence, revealing how planets actually form, migrate, and evolve across the galaxy. The first surprise was not especially encouraging for simple expectations about habitability. Hot Jupiters demonstrated that giant planets could migrate inward after their formation, disturbing the regions where rocky planets might otherwise emerge. Instead of assuming every sun, like star, possessed an orderly arrangement resembling our own solar system, astronomers now had compelling evidence that many systems followed dramatically different histories. At the same time, another uncertainty disappeared entirely. No longer could anyone seriously argue that the solar system might be the only planetary system around a sun-like star. Planets were undeniably real beyond our cosmic neighborhood. The debate shifted from whether they existed to understanding what kinds of planets were most common and which environments might allow life to persist. This transformation reached even into one of astronomy's best-known thought experiments. In 1961, astronomer Frank Drake introduced what became known as the Drake equation, a framework for estimating the number of communicating civilizations within the Milky Way. One part of that equation represents the fraction of stars possessing planetary systems. When Drake first proposed it, nobody knew the correct value. It could only be estimated. Today, that particular uncertainty has been greatly reduced. Extensive surveys now indicate that planetary systems accompany essentially all stars. One important variable has therefore changed from informed speculation into an observational result. Yet resolving one uncertainty exposed several others with greater clarity. Astronomers now devote increasing attention to questions that remain unanswered. How many planets actually reside within habitable zones? On how many of those worlds does life begin? How often does simple life evolve into complex organisms and eventually into intelligent civilizations capable of observing the universe around them? Those quantities remain unknown despite the remarkable expansion of our planetary census. As more discoveries accumulated, the galaxy appeared increasingly crowded with worlds. Yet those same observations revealed countless planetary architectures unlike our own, introducing additional filters that may reduce the number of environments suitable for long-lived life. You could say that 51 Pegasi b narrowed ignorance without eliminating mystery. It transformed a timeless question into a scientific investigation guided by observation, evidence, and the diverse planetary systems that continue to reshape our understanding of where life might, or might not, find a lasting home. Long before astronomers could count planets across the galaxy, another search had already begun. In 1960, astronomer Frank Drake aimed a radio telescope toward two nearby sun-like stars and listened for 6 weeks. The effort became known as Project Ozma, the first modern scientific search for extraterrestrial intelligence. Nothing unusual appeared in the data, Yet the experiment established a new way of asking one of humanity's oldest questions. The search never truly stopped. Over the following decades, increasingly capable observatories examined hundreds of carefully selected stars, while wide field surveys scanned enormous portions of the sky. Billions of radio frequency channels have been monitored, and years of observations have accumulated across many different listening strategies. Despite this remarkable effort, no confirmed signal has been identified as originating from a technological civilization beyond Earth. That absence gave renewed attention to an idea raised during a lunchtime conversation in 1950 by physicist Enrico Fermi. His question became known as the Fermi paradox. If the Milky Way contains hundreds of billions of planets, and if life commonly emerges wherever conditions permit, why has no unmistakable evidence of another civilization appeared? Where is everyone? Several possibilities have been proposed. Perhaps humanity has listened for only a brief moment compared with the age of the galaxy. Radio technology itself has existed for little more than a century, an interval almost insignificant on cosmic timescales. We may also be searching at the wrong frequencies or overlooking forms of communication unlike anything our own civilization has invented. Other explanations are less encouraging. Intelligent life may be exceptionally uncommon, even if simple organisms are widespread. Civilizations might disappear before developing technologies capable of long-distance communication or before choosing to broadcast their existence across interstellar space. The growing census of exoplanets has added another important piece to this puzzle. Hot Jupiters revealed that some planetary systems lose their inner rocky worlds through giant planet migration. In those systems, the conditions favorable for Earth, like planets, may never exist. Entire branches of the galaxy's planetary population could therefore be unsuitable for life before biology has any opportunity to begin. Astronomers have also identified additional stages that may represent difficult evolutionary thresholds. The emergence of complex cells, the transition to multicellular organisms, the development of sexual reproduction, the persistence of stable continents above global oceans, the presence of a large moon capable of moderating planetary rotation, and plate tectonics that continually recycle carbon through the atmosphere may each contribute to long-term habitability. Whether any of those steps are genuinely rare remains unknown. As you follow this chain of possibilities, the unanswered question becomes more carefully defined rather than more mysterious. The continuing absence of a detected signal does not demonstrate that humanity is alone. It is equally compatible with a galaxy where intelligent civilizations are separated by immense distances, where they communicate through methods we have not yet recognized, or where our brief period of listening has simply not overlapped with theirs. For now, the universe continues to answer with data, while leaving its deepest conclusion unwritten. Some discoveries reveal their importance almost immediately. Others require decades before their full meaning becomes unmistakable. The discovery of 51 Pegasi b belonged to the second kind. Although the announcement in Florence changed astronomy in 1995, the highest recognition arrived only after an entire generation of scientific work had confirmed what that first observation truly represented. On the 8th of October, 2019, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Michel and Didier Queloz for the discovery of an exoplanet orbiting a solar-type star. The prize was shared with cosmologist James Peebles, whose theoretical research into the structure and evolution of the universe had transformed our understanding of the cosmos on the largest scales. Together, The awards recognized complementary advances that deepened humanity's understanding of its place within the universe. By the time of the ceremony, Michel was 77 years old. Didier Queloz was 53. More than 2 decades earlier, Queloz had been a doctoral student patiently processing telescope observations, searching for subtle patterns buried within streams of numerical measurements. The signal that eventually emerged appeared so unexpected that confidence came only through relentless verification. The Nobel Committee described their achievement with remarkable restraint, referring simply to the discovery of an exoplanet orbiting a solar type star. Those few words accurately identified the accomplishment while leaving its enormous consequences unstated. From that single detection grew an entirely new branch of astronomy, one that eventually revealed thousands of distant worlds and fundamentally altered our understanding of planetary systems. The passage of 24 years was neither unusual nor accidental. Nobel Prizes are rarely awarded immediately after a major discovery. Time allows independent observations to confirm the original result, competing explanations to disappear, and the broader significance to emerge through continued investigation. By 2019, more than 4,000 exoplanets had been confirmed. The existence of planets around other sun-like stars was no longer surprising. It had become one of the defining foundations of modern astronomy. After receiving the prize, Michel spoke publicly about the possibility of life elsewhere in the universe. He carefully distinguished personal belief from scientific evidence, explaining that he believed life almost certainly exists beyond Earth, while acknowledging that observation had not yet provided proof. His confidence reflected the expanding census of planetary systems rather than any confirmed detection of biology. Didier Queloz later described the original discovery in similarly measured terms during his Nobel lecture. He recalled that triumph was not the first emotion, confusion came first. Instrument malfunction seemed more likely than an entirely new kind of planetary system. Stellar activity became the next possibility. Only after systematically eliminating every alternative explanation did the extraordinary conclusion remain. As you look back across that interval, the award itself becomes part of the story. The waiting was never a delay in recognizing the discovery. It was the scientific method unfolding at its natural pace, allowing one unexpected signal to mature into one of the most firmly established revolutions in modern astronomy. The pace of discovery can sometimes be measured by generations. In the search for planets beyond our solar system, it has unfolded within a single human career. What began with a faint stellar wobble has grown into the ability to examine the chemistry of distant atmospheres, revealing a transformation that few astronomers in 1995 could have imagined. At the beginning, the information was remarkably limited. A spectrograph at the Haute-Provence Observatory in France detected the periodic motion of a star. From that subtle movement, astronomers determined that a planet existed. They could calculate its orbital period, estimate its minimum mass, and determine its distance from the parent star. Beyond those fundamental properties, the world itself remained hidden. Only 7 years later, the Hubble Space Telescope crossed another threshold. In 2002, it detected sodium vapor within the atmosphere of the exoplanet, hydrogen delta 2 09458b. For the first time, astronomers identified the atmosphere of a planet orbiting another star. Atmospheric characterization, the study of a planet by examining the composition of its atmosphere, had begun. Progress continued at an astonishing pace. During 2005, The Spitzer Space Telescope directly measured infrared radiation, a form of heat energy, from a hot Jupiter. Observations made throughout an orbit gradually developed into phase curves. Measurements collected as different portions of a planet rotate into view, allowing astronomers to estimate temperature distributions across alien worlds. Between 2009 and 2013, the Kepler Space Telescope expanded the field beyond remarkable individual discoveries. Thousands of confirmed planets transformed isolated detections into population studies, revealing broad statistical patterns across many different types of stars and planetary systems. Another major advance arrived in 2018 with the launch of the Transiting Exoplanet Survey satellite. Unlike Kepler, which concentrated on one carefully selected region of the sky, this mission surveyed an area roughly 400 times larger, while focusing on bright nearby stars that ground-based observatories could investigate in greater detail. The following years demonstrated how rapidly those discoveries could mature. In 2020, the Michel spectrograph for rocky exoplanets and stable spectroscopic observations provided the first direct observational evidence of iron rain within the atmosphere of WASP 76b. 1 year later, the James Webb Space Telescope began its journey into space. By 2022, its extraordinary sensitivity revealed carbon dioxide within the atmosphere of WASP 39b with unprecedented clarity. More recently, observations of K2 18b have identified a possible signature of dimethyl sulfide, a molecule produced by marine organisms on Earth. The interpretation remains preliminary, actively debated, and scientifically unresolved. Even so, it represents one of the closest approaches yet to identifying a potential biosignature beyond our solar system. When you trace this progression across only 3 decades, the change is remarkable. Astronomy has advanced from asking whether a distant planet exists to investigating the chemistry of its atmosphere and considering whether those chemical fingerprints could someday reveal the presence of life. The next step is already taking shape through plans for the Habitable Worlds Observatory, a future mission intended to directly image rocky planets around nearby stars and search their atmospheres for possible biosignatures. If you could travel beyond the moon, far past the orbit where most satellites circle Earth, you would eventually arrive at a location where gravity itself helps hold a remarkable observatory in place. There, approximately 930,000 miles from Earth, the James Webb Space Telescope circles the second Lagrange point, a region where the combined gravity of Earth and the Sun allows the telescope to maintain a stable orientation while keeping its enormous sun shield permanently facing the sunday. Everything about the observatory was designed to preserve extreme sensitivity. Its primary mirror stretches 21 and 3/10 feet across and collects roughly 2 and 7/10 times as much light as the mirror aboard the Hubble Space Telescope. Rather than a single piece of glass, the mirror consists of 18 gold-coated beryllium segments that unfolded after launch and align themselves with astonishing accuracy. Each segment must be positioned to within mere nanometers, distances so small that they are measured in billionths of a meter, allowing the separate pieces to function as one continuous mirror. The telescope observes primarily in infrared light, wavelengths beyond human vision that carry valuable information about cool objects, distant galaxies, and the atmospheres of planets orbiting other stars. Many important molecules absorb infrared light at specific wavelengths, leaving unmistakable fingerprints within the spectrum of a planet as starlight passes through its atmosphere. For exoplanet science, That capability has transformed what astronomers can measure. The James Webb Space Telescope can identify signatures from water, carbon dioxide, methane, sulfur dioxide, and potentially nitrous oxide with a precision that earlier space observatories could never achieve. Each detected molecule adds another clue to the chemistry, temperature, and physical processes shaping an alien atmosphere. One of the earliest demonstrations arrived during observations of WASP 39b, released during the summer of 2022. Its transmission spectrum, a record of starlight filtered through the planet's atmosphere during transit, revealed water, carbon dioxide, sodium, potassium, and sulfur dioxide together. Sulfur dioxide proved especially important because its presence indicated active photochemistry, meaning energetic starlight was driving chemical reactions high above the planet's cloud tops. More recently, observations of K218b suggested the possible presence of dimethyl sulfide. The interpretation remains preliminary and actively debated within the scientific community. Even so, the telescope demonstrated that it can search for molecules present at only a few parts per billion within the atmosphere of a planet, approximately 120 light years away. That level of sensitivity was largely theoretical only a few years earlier. Current estimates indicate that the James Webb Space Telescope carries enough fuel to continue station keeping for roughly 2 decades. During that time, biosignature research will continue advancing at an extraordinary pace. Although 51 Pegasi b itself cannot be studied easily through transmission spectroscopy because of its orbital geometry, every hot Jupiter examined by the telescope strengthens the atmospheric models that help us understand the first world that changed exoplanet science forever. Humanity has revised its place in the universe many times. Each revision has begun with a single observation that seemed modest at first, then gradually expanded until it reshaped our understanding of everything surrounding it. The discovery of 51 Pegasi b belongs to that continuing sequence, another reminder that the cosmos rarely arranges itself according to our expectations. The first great shift arrived when Nicolaus Copernicus proposed that Earth travels around the Sun rather than occupying the center of creation. Centuries later, astronomers recognized that the Sun itself follows an immense orbit around the center of the Milky Way, joining several 100 billion other stars in a vast galactic system. During the 1920s, Edwin Hubble demonstrated that the Milky Way is only one galaxy among hundreds of billions scattered across the observable universe. Each discovery expanded the stage while reducing the special status of what had once appeared unique. For much of the late 20th century, one assumption remained largely untouched. Although astronomers expected planets around other stars, the solar system was treated as the natural blueprint for planetary formation. Rocky worlds close to the star, giant planets farther away, nearly circular orbits, and broad stability seemed likely to represent the ordinary outcome whenever a planetary system assembled from a disk of gas and dust. Then observations began telling a different story. The growing catalog of exoplanets revealed architectures that often bore little resemblance to our own. Giant planets circled their stars within only a few days. Some worlds traveled along highly elongated paths. Compact systems contained multiple large planets orbiting much closer together than Mercury lies to the Sunday. Super-Earths, planets larger than Earth, yet smaller than Neptune, appeared throughout the galaxy despite having no equivalent within our own planetary family. As the census expanded, our solar system changed from the expected pattern into one example among many. The broad gap between Mars and Jupiter, the absence of super Earths, Jupiter's distant and nearly circular orbit, and the orderly spacing of the inner rocky planets no longer appeared to be universal features. They became characteristics of one particular history, shaped by conditions that need not be repeated elsewhere. You might wonder whether this makes our solar system unusual in an unfavorable sense. The evidence suggests something more balanced. Statistical rarity does not imply weakness, superiority, or inevitable destiny. It simply means that nature is capable of producing a wider range of planetary systems than earlier generations imagined. Replacing an incorrect expectation with one supported by observation represents scientific progress, regardless of whether the conclusion flatters our intuition. Across each stage of this long intellectual journey, the pattern has remained remarkably consistent. A familiar picture places humanity or its surroundings near the center. New evidence challenges that picture. Debate follows, sometimes for years. Eventually, the observations accumulate until the broader view becomes unavoidable. Within that sequence, 51 Pegasi b occupies a lasting place. It was more than the first confirmed planet orbiting a sun-like star. It marked another step in the continuing realization that the universe is richer, more varied, and less centered upon our own experience than we once believed. Numbers can become so large that they lose their meaning. We speak them with ease, yet our intuition cannot truly contain them. To understand what separates us from 51 Pegasi b, we have to slow those numbers down until they become something we can follow. The planet lies approximately 50 and 9/10 light years from Earth. A single light year represents roughly 5 and 88 hundredths trillion miles, the distance that light itself travels through empty space in 1 year. Together, those figures place 51 Pegasi b nearly 299 trillion miles away, a span so immense that even our fastest achievements begin to appear almost motionless against it. Consider the most distant object humanity has ever built. Voyager 1 continues moving away from the Sun after decades of travel and now resides approximately 15 billion miles from Earth. Its speed is roughly 38,000 miles per hour, astonishing by everyday standards. Yet maintaining that pace without interruption, it would require approximately 900,000 years to arrive at 51 Pegasi b. Entire branches of human history would rise and disappear before the spacecraft approached its destination. Suppose instead that we imagined a vehicle capable of reaching 1/10 of the speed of light, a velocity no human technology has remotely achieved. Even then, the crossing would require approximately 509 years. The travelers who departed would never witness their arrival. Generations would inherit the journey long before anyone inherited its destination. Even our nearest confirmed exoplanet remains almost unimaginably distant. Proxima Centauri b orbits its small red star approximately 4 and 24 hundredths light years from Earth, roughly 25 trillion miles away. At Voyager 1's present speed, reaching that neighboring world would still demand approximately 75,000 years. Meanwhile, the catalog of known exoplanets continues growing. More than 5,700 have now been confirmed. We have visited exactly none of them. Every discovery has come through another messenger. We send light, and we receive light. Radio waves reveal stellar motion. Reflected starlight exposes atmospheric chemistry. Tiny changes in brightness uncover planets crossing distant suns. Information crosses the darkness, while our spacecraft remain close to home. Humanity has transmitted only a handful of deliberate greetings into the galaxy. Among the most famous is the message broadcast from the Arecibo Observatory during 1974, aimed toward a distant star cluster approximately 25,000 light years away. Today, that transmission has traveled only about 51 light years. It will continue for another 24,950 years before reaching its intended destination. Even an immediate reply would require another 25,000 years to return. As you reflect upon those intervals, the distances between stars reveal themselves as something fundamentally different from every journey in human experience. They are not merely larger versions of voyages across oceans or continents. They belong to another category entirely, demanding technologies and civilizations far beyond anything we possess today. We know that 51 Pegasi b exists. We have measured its orbit, studied its atmosphere through models refined by neighboring worlds, and traced the chemistry of similar planets across the galaxy. Yet one truth remains unchanged. We will almost certainly understand its storms through light alone, never beneath their skies. Some destinations become more meaningful because we know we can never live there. 51 Pegasi b belongs to that category. Every observation gathered across the past 3 decades points toward a world of overwhelming heat, powerful radiation, violent atmospheric circulation, and chemistry profoundly incompatible with biology as we understand it. Its future is equally unforgiving, ending when its aging star eventually expands and consumes the planet altogether. Yet that conclusion carries an unexpected consequence. Discovering one of the least hospitable planets known does not narrow the possibilities for life elsewhere. It broadens our understanding of what planetary systems can become. Nature is capable of producing environments across an astonishing spectrum, extending from worlds where life appears impossible to others that may possess far gentler conditions. As astronomers refine their search, certain characteristics continue to emerge as especially promising. The strongest candidates are small, rocky planets orbiting within the habitable zones of stable G-type or K-type stars, where temperatures may allow liquid water to persist on the surface. Systems that avoided the inward migration of giant planets appear especially favorable, preserving their inner rocky worlds. Additional ingredients may include a substantial magnetic field to deflect charged particles from the host star, plate tectonics that continually recycle carbon through the atmosphere, and perhaps a large moon that helps stabilize long-term changes in planetary rotation. Earth satisfies every one of those conditions. No other confirmed planet currently does. Several worlds satisfy part of the list, encouraging astronomers to investigate them with increasing precision while recognizing that important pieces of the puzzle remain missing. Among the most intriguing examples is the TRAPPIST-1 system, located approximately 40 light-years away. 7 rocky planets orbit its small red dwarf star, with at least 3 residing within the traditional habitable zone. Every one of those planets is believed to be tidally locked, keeping one hemisphere permanently facing the star. Whether that arrangement prevents habitability or simply produces unfamiliar climates remains an active area of research rather than a settled conclusion. Another compelling target is K218b, approximately 120 light-years from Earth. Water vapor has been confirmed within its atmosphere, and some models suggest the possibility of an ocean beneath a deep hydrogen envelope. Whether liquid water truly exists, there remains uncertain. Whether any environment beneath those clouds could support life is equally unresolved. As you follow these discoveries, the search itself has changed beyond recognition. It no longer rests upon philosophical speculation alone. It has become a scientific program built around observatories, carefully selected targets, increasingly sophisticated instruments, and measurable questions attached to specific stars scattered across the night sky. No one can say whether convincing evidence for life beyond Earth will emerge during our own lifetimes. Science offers no timetable for discoveries of that magnitude. What it does offer is something equally valuable, a method that continues to replace uncertainty with evidence, one distant world at a time, revealing a universe whose diversity is far greater than anyone standing beneath Earth's skies once imagined. Among all the ways humanity has learned about the universe, astronomy occupies a place unlike any other. Every mountain we have climbed, every ocean we have crossed, and every landscape we have explored eventually yielded to physical presence. Distant planets ask something entirely different of us. They invite understanding without arrival, replacing footsteps with measurements carried across unimaginable distances by light alone. That is the relationship we now have with 51 Pegasi b. We know the temperature of its dayside. We have estimated the circulation of its atmosphere, inferred the chemistry of its iron rain, constrained its mass, reconstructed its structure, and refined models describing the layers above its hidden depths. Altogether, those observations amount to a remarkably detailed portrait of a world nearly 299 trillion miles from Earth. None of that knowledge came from traveling there. No spacecraft has approached the star. No probe has crossed the darkness between our solar system and Pegasus. Every discovery began with photons, individual particles of light that departed the 51 Pegasi system more than 50 years before reaching Earth. Along their journey, those photons carried tiny changes in brightness, color, and wavelength, preserving information about the atmosphere and star they encountered before continuing across interstellar space. In that sense, we never truly went to 51 Pegasi b. Its story arrived here instead, one photon after another, collected by mirrors polished to extraordinary precision and detectors sensitive enough to recognize patterns hidden within streams of ancient light. Generations of astronomers learned how to read those patterns, transforming faint signals into knowledge that no human eye could perceive unaided. There is something remarkable about that kind of understanding. We can know a place without touching its clouds. We can describe weather beneath a sky no person has seen directly. We can calculate conditions on a distant planet while remaining permanently separated from it by distances that current technology cannot overcome. This has become humanity's primary relationship with the wider universe, profound familiarity across expanses that remain physically unreachable. Whether future civilizations narrow that separation is impossible to predict. Centuries from now, people may possess capabilities that seem inconceivable today. They will inherit questions we cannot yet imagine, along with technologies that do not presently exist. Those possibilities belong to a future still unwritten. One truth, however, remains independent of every observer. Long before telescopes existed, the star was shining. The planet continued its rapid orbit. Iron condensed within its atmosphere and fell through alien skies. Those events unfolded without witnesses, following the same laws of nature that govern every corner of the cosmos. Our observations did not create that distant world, they uncovered it. That achievement became possible because people devoted decades to building better instruments, studying a seemingly ordinary star in the constellation Pegasus, and trusting evidence even when it challenged familiar ideas. From that patience emerged one of humanity's deepest forms of knowledge, understanding a world we may never visit, yet know with extraordinary clarity. Step back far enough, and even galaxies begin to resemble grains scattered across an immeasurable expanse. Our perspective widens until familiar landmarks disappear, replaced by numbers so immense that language struggles to contain them. Yet those numbers describe the setting in which every star, every planet, and every observer exists. Current estimates suggest that the observable universe contains roughly 2 trillion galaxies. Within only one of them, the Milky Way, reside approximately 100 billion to 400 billion stars. Extending that count across the observable universe leads to an estimate of roughly 700 sextillion stars, a number written as 7 followed by 23 zeros. If only a modest fraction of those stars possess planetary systems, then the total population of worlds exceeds any quantity that carries a commonly used name. Against that immense backdrop, 51 Pegasi b appears almost vanishingly small. It is one entry within a census so vast that the human mind naturally compresses it into abstraction. Large collections become statistics. Individual worlds disappear behind extraordinary totals. Yet this planet refuses to remain anonymous. We know when it was discovered. We know the astronomers who recognized its signal. We know the length of its year, the approximate mass hidden beneath its atmosphere, the character of its weather, and the physical processes shaping the gases surrounding it. These measurements transform a distant object into a genuine place, one with properties that distinguish it from every other world orbiting every other star. The universe itself makes no distinction between places that attract attention and those that never will. It forms hot Jupiters, frozen rogue planets drifting between stars, dense molecular clouds where future suns are born, and galaxies that collide over millions of years. None of these events require an audience. They unfold according to the same physical laws whether anyone observes them or not. What deserves reflection is something different. Those same laws also produced a small rocky planet orbiting a stable star, where chemistry became biology, biology became intelligence, and intelligence learned to polish mirrors, build spectrographs, and recognize the tiny wobble of a star approximately 50 light years away. The Nobel Prizes that followed, the observatories spread across Earth and beyond it, and even this shared moment of contemplating the cosmos all emerged from that single chain of physical events. As you consider that sequence, an extraordinary symmetry begins to appear. The same universe that generated stars and planets also generated minds capable of asking what those stars and planets are like. Physics shaped both the distant world and the observers who eventually understood it, linking them across interstellar space through nothing more than light and patience. Whether that convergence is common throughout the cosmos or exceedingly rare remains unknown. The growing census of exoplanets has brought us closer to answering the question than any previous generation could have imagined. Even now, however, the deepest mystery remains wonderfully intact, waiting among countless worlds that still shine beyond the reach of our understanding. On a clear evening beneath dark skies, far from the glow of cities, you can look toward the constellation Pegasus. During late summer, it rises above the horizon, climbing higher as autumn advances across the northern hemisphere. Within that familiar pattern rests a faint point of light with an apparent magnitude of 5 and 49, lingering near the limit of what unaided human vision can perceive. It appears ordinary. Nothing about its gentle glow suggests that it changed astronomy forever. That star has been shining for approximately 5 and 9/10 billion years. It began producing light before our own sun formed, before Earth existed, and before the earliest chapters of our planet's history unfolded. While multicellular life was only beginning to emerge in Earth's ancient oceans, its light was already crossing space exactly as it does today. Orbiting astonishingly close to that star is 51 Pegasi b. It completes another year in only a few Earth days. Iron has condensed within its atmosphere and fallen through its skies for ages beyond imagination. Winds have raced through its atmosphere at speeds approaching 9,000 miles per hour for billions of years. The same hemisphere has remained turned toward its star since long before our own solar system settled into the arrangement we now call familiar. None of those events waited for observers. They unfolded through immense stretches of cosmic history, while no living creature on Earth possessed the ability to imagine another planetary system. They will continue long after every generation alive today has passed into history. Then, during October of 1995, something changed. The planet remained exactly where it had always been. Its star continued shining without interruption. The orbit did not shift. The atmosphere did not transform. Instead, the change occurred here. Two astronomers examined an unexpected pattern hidden within careful measurements of starlight. Existing theories offered little room for such a result, yet Michel and Didier Queloz chose to follow the evidence rather than dismiss it. That decision opened a path unavailable to every civilization before them. Humanity crossed from believing other planetary systems probably existed to knowing that they did. Since then, more than 5,700 confirmed exoplanets have joined the growing catalog, each adding another chapter to a story that continues unfolding across the galaxy. One day, those observations may reveal persuasive chemical evidence that biology exists beyond Earth. They may instead show that living worlds are extraordinarily uncommon. Either conclusion would reshape our understanding of life and our place within the cosmos because both answers arise from evidence rather than speculation. Tonight, the star still shines within Pegasus. The planet continues its rapid orbit. Iron still falls through an atmosphere no human being will ever enter. The universe carries on exactly as it did before anyone noticed. The difference is that now you have shared in one of humanity's most remarkable discoveries. A distant point of light is no longer merely another star. It has become a known world, patiently revealing its story across 50 light years, one photon at a time.